Okay, so we are in this book up here, Generalized Linear Models with Examples in R, and we are on question 2.14, 214. This is a long question with many parts, so we'll just read each part as we come to it. But what's important here is that we're given some, not really data, but we're given the output of a regression that has been ran. And so what we're given then is a table of the coefficient estimates, beta, as well as their standard errors. Okay, and what is being measured here, or what is being analyzed, is blood pressure regressed on these various predictor variables here. Okay, and so it's for those predictor variables that we have our beta coefficients. Okay, and so we're going to go through some questions here, but we're going to have an eye on the effect of ambient temperature on blood pressure after controlling for some of these other variables here. Okay, so for part one, we are meant to compute the p-values for each term in the model and then comment, right? So for each one of these beta coefficients, which corresponds to a predictor variable, we are meant to find a p-value, again representing the relationship between the predictor variable with blood pressure, systolic blood pressure. Okay? So how do we do this? So for each one of the beta estimates, we go through and we calculate our t-statistic, okay, which is given here. It's the estimate minus the null estimate, which I'm going to take to be 0 in all cases here. In other words, that the beta coefficients equal 0. We could define a different null hypothesis for these, but we'll just use mean 0. And all that divided by the standard error, that's going to give us our t-statistic. And then with that t-statistic, we will compare it to the t-distribution and see how probable it is that that t-statistic could have been generated from the null hypothesis. Okay. So I'm going to do all of this in R rather than by hand. I think that's maybe more instructive in this context. So first I'm going to put all of our data into a data frame here. Okay, so this is just the same information that I've typed up here, put into a table up there. Okay. So this is what we get. All right. And now I'm going to calculate the t-stat for each of these. Okay, so I just take my formula up here. So I take the beta from my data frame, and I'm subtracting 0, right? So I'm not putting minus 0 here, right? Because d beta minus 0 is just d beta. And then divided by the standard error. And I'm just rounding all of this so that we don't have 10 different digits. So we're not trailing 10 digits here, okay? So now I have the data frame plus my t-stat over here. And I'm going to calculate the p-value, all right? So to calculate the p-value, I need to compare it to a t-distribution, but there is a different t-distribution for every degree of freedom that we could have. So first I need to find the degrees of freedom. Sometimes that's denoted as nu here, this Greek letter nu. Okay. So we're told that there's 574 observations, right? So the question tells us that we have 574 observations. To get our degrees of freedom, we need to subtract p prime, which means each coefficient here, or each predictor variable plus the constant, right? So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, right? So I need to subtract 6 from 574, so that's my degrees of freedom. And then to calculate my p-values, again, all of this is just in a round function, just so I'm not trailing a bunch of digits, okay? But I'm going to take 1 minus 1 minus the cumulative t-distribution, okay, of my t-stat with this many degrees of freedom. Okay, so when I do all of that, now I have my p-values over here. Okay, Okay, so now I want to discuss the relationship between each of my predictor variables with systolic blood pressure. Okay, so so after adjusting for all other predictive variables, what is the relationship between ambient temperature and systolic blood pressure? Okay, so we're looking at this right here. So after accounting for all other variables, systolic blood pressure is predicted to decrease by about 0.5 point for every 1 degree increase in ambient temperature. Okay, that's what that means. Okay, and it has a standard error of 0.262. Okay, and this relationship has a p-value of 0.0472, or stated differently, if the null hypothesis were correct, in other words, that temperature had no relationship with ambient temperature, then the probability of seeing our data is about 4.72%. Okay. All right. So now we want to plot a line describing the relationship between ambient temperature and systolic blood pressure, and we want to do this for a man that is 30 years old who doesn't smoke or drink alcohol and has a waist circumference of 100 centimeters. Okay. Now the authors apparently state that temperatures range from 20 to as high as 45. All right. So I'm actually going to go all the way to 0, but in other words, we need to plot the relationship across some temperatures. Okay. And so I'm going to well, I'll get there in the code. So we're going to use this information to make a plot. All right. So to do this, the first thing I need to do is I need to define values for each of the predictor variables, except for the one that we're trying to predict here, right? Which is ambient temperature. Okay. So I'm assigning these values here. So let me just show you what's going on. So it's 1, 30, 100, 00, and A. So the 1 corresponds to the constant. 30 corresponds to age, 100 to waist, 0 and 0 for these indicator variables of alcohol and smoking, and then the temperature is the thing that we're trying to graph the relationship with. Okay, so I just assign a value to each of those variables, and then I have a sequence of temperatures from 0 to 45, and so I'm gonna go to each 1 degree, or I'm going to go from 0 to 1 to 2, so every centigrade increase in temperature. Okay. And now I'm just going to plot this. So for every temperature, I'm going to have a systolic blood pressure. Okay. So how do I do that? Well, I take this. Well, let me get there in just a second here. So I found a little error there that I have to correct. But so I'm gonna have a sequence of systolic blood pressures, okay, 1 for each degree centigrade. Okay, so for this, I'm going to take the beta for the case value, okay, right? So again, I'm going to take the coefficient times the value that I've assigned to that predictor variable, and those just get multiplied, and then I sum those together, okay, and then because my case has an NA, it's going to produce NAs, and if you try to sum where there's an NA, you return NA. So in order to ignore the fact that I have an NA in my case values, I put NA RM equals true. Okay, and then to that, I add the sixth row of my beta values, which corresponds to temperature, the effective temperature, multiplied by every value and temperature sequence. Okay, I've already ran this, but this is what you get. So as I go from 0 to 45 degrees centigrade, you are on the y-axis. You are seeing the relationship then with systolic blood pressure, right? So as I get hotter, my systolic blood pressure drops. In this, well, it's linear, but it's linear given the assumptions of the model here. Okay. All right, so now I need to compute 95% confidence intervals. Okay, so I'm defining my 95% confidence interval. Then I need an alpha term, which is 1 minus this, so 0.05. Okay, and then I need to divide that by 2. And so now I need to find I need to find a t-value, okay, where so let me say this again. So I need to find the quantile of my t distribution. Which t distribution? The one with df degrees of freedom. Okay, that corresponds to 1 minus a over 2. Okay. All right. So so for the low confidence interval, I have d beta minus t value times the standard error, which this is just a formula for my confidence intervals as well as for the high, right? So I'm adding the the margin there. Okay. So when I do that, so this is what we have now. So here's my low confidence interval and my high confidence interval, okay, for each of the variables. And so now on to part 5. So I'm not really sure what this question is asking. If you have a better sense, then please leave a comment. But we need to interpret the relationship between ambient temperature and all other variables in the regression equation. So I'm not really sure what this is asking for. It has already asked for the relationship between blood pressure and ambient temperature after controlling for these variables. So I'm not really sure what is being asked about the relationship among the variables, right? So we'd actually need, I think, raw data to look at like a pairs plot or something like that. And so the best that I could come up with here is to restate the answer that I already gave, describing the relationship between temperature and blood pressure, but just emphasize after accounting for the other predictor variables here. Okay, so yeah, so like I said, I'm not really sure what this is asking for. So if you have a better answer, please let me know. Okay, so last part. So now we're supposed to predict the blood pressure, the mean blood pressure. That's important. For a 35-year-old man, Ghanaian man, who doesn't smoke, drink, and has a waist circumference of 100 centimeters in ambient temperature of 30 degrees Celsius. Okay, so this will look very similar to what we already did, here in part 3, right? So I'm going to assign a value to each of my coefficients, but now I will actually have a coefficient for temperature, which is, I think, 35 degrees. And then I will multiply each of those together, right? So I'm defining the value for each one of those variables, and then each one of those variables is being multiplied by its respective beta coefficient, and then I just sum all of that together. Okay? And so that tells me then that that the predicted blood pressure given those conditions is about 138 millimeters of mercury. Okay, that is it.